Hi, it's Dr. Harris again with the second video in Chapter 1 of our Math 111 statistics course. We're still working through an introduction to data. And in this slideshow, we're going to be talking about two means of processing data, of looking at data and trying to say intelligent things about the data that we collect in the populations that we're studying. So the first of these is going to be an observational study. So let's talk about observational studies for a little bit. This is where, as you can see in what I've written here, researchers are gathering data without imposing anything on the people, the subjects that they're collecting data from. We're just merely collecting data. And as an example, we looked at the NHANES 18 data set in our previous slideshow. That would come from an observational study. We're just collecting health information about a large number of individuals. One important thing that we wanted to really focus on and absorb from looking at observational studies is that if we're examining two variables and we're noticing some relationship between the variables, we're not going to be able to establish a causal relationship between the two variables from an observational study. And by causal relationship, we mean that the values of one of the variables, the explanatory variable changing, is not necessarily driving changes in the response variable. We'll be talking about another type of study that allows us to draw causal relationships in a few slides. But anytime you want to look at data and analysis of data, you want to be first asking, does the data come from an observational study? If the answer is yes, then we're not going to be able to draw any sort of causal relationship. So really try to keep that in mind as we go through these questions, these examples. So here's a big reason why we're not able to draw a causal relationship from observational studies. And that is that there could be a third variable that we're not directly studying that could be having an impact on both our explanatory and our response variables. And so I want to give you a few examples of where confounding variables can arise. One of them comes from our text on page 25. Suppose that you were looking at sunscreen use by a collection of individuals and long-term incidence of skin cancer in those individuals. And you discovered that the people who used sunscreen more frequently had skin cancer more frequently. So increased use of sunscreen seemed to be associated with increased incidence of skin cancer. So from that study, should we be able to draw a conclusion that sunscreen use seems to lead to skin cancer? Should we just avoid skin cancer by not using sunscreen? Something doesn't seem quite right to us about that, I hope. But after thinking about it for a little while, what you might realize is that there's a third variable that's not directly under study here that could be driving the skin cancer, and that is how much time one spends out in the sun. And so people who spend time out in the sun are probably going to be using sunscreen more frequently than other folks. And if they're out in the sun, they're probably at higher risk for getting skin cancer. And so we want to be aware of situations like this where it seems like we've got maybe a causal relationship on the surface, but if we drill down a little bit, we can think there might be a third variable not under study that's driving the relationship. So let's think about confounding variables a little bit more and causation. So here's how we can think about causation. Let's look at this last sentence here on this slide. If two individuals are alike in every way except for one variable and they have different outcomes, then we're more likely to think that one variable in which they're different, it could be actually causing the difference in response. And so the example here is if you think about how fast one drives on average on the highway and how many speeding tickets one gets over a time period, we would say that speed, how fast you go, is causing the number of tickets you get if it's the case that if two individuals are alike in every way except for how fast they go on the highway, and the one who goes faster gets more tickets, then we might think that, yeah, maybe getting speeding tickets is somehow related to how fast we drive. Another example is the relationship between smoking and lung cancer. If explanatory variable is whether or not one smokes, and our response variable is whether or not one in the long term has lung cancer, we would say that smoking causes lung cancer if two individuals are alike in every way except for whether or not they smoke. And if the one who smokes winds up getting lung cancer, then we would tend to think that maybe the smoking was the driving force here. So just a tiny bit more on confounding variables. Let's let x be our explanatory variable, y be our response. A third variable, z, is going to be confounding if it's associated with the explanatory variable but not caused by it. But this third variable helps to actually cause values in the response variable itself. So it's more the causal variable. And so we want to be on the lookout for these confounding variables because they are frequently going to be present in observational studies. One more example related to driving on the highway and getting tickets. An observational study determines that people who drive brightly colored cars are more likely to receive tickets than people who drive a more sedate color. And so should we think that car color is actually attracting the attention of police and causing them to maybe pay more attention to those folks and ticket them more frequently? You hear this almost sort of an urban legend type of thing, but there's a confounding variable that could be involved here, and that is how one behaves behind the wheel. It could be that people who like to drive fast want to drive a car that goes fast, and those cars tend to come in bright colors more frequently, your reds, your yellows, and so on. And so it's not the color of the car they're driving, but the fact that the cars that they kind of like to drive come in those colors that would be causing them to get more tickets. So that's not to say that we can't draw conclusions from observational studies. It's just that we can't draw causal conclusions from them. And so we want to think about what can we do that would allow us to actually observe relationships from observational studies, even if we're not saying that they're causal relationships. And so this comes down to, can we trust that the individuals that we collect the data from represent the population? So if remember that we're generally not going to be getting information from everybody in the population. We're going to be drawing a sample. And so we want to draw what we would call a representative sample from the population. And so how can we most likely ensure that our sample can be considered to be representative of the population? So let's consider a couple of options here. One would be to let people opt into participating in the study, and this would be called a volunteer sample. And so suppose that you students at Georgetown College want to conduct, not conduce, a survey on food in the calf. And so if you left survey forms at the entrance and let people choose whether or not to participate, we have to think, well, is that going to give us a representative sample of student opinion across campus? It might, but we can't really count on it. People who tend to fill out surveys tend to have strong opinions. And so those strong opinions may or may not represent the range of opinions that we would have on campus. And so generally speaking, volunteer samples, letting participants opt in, aren't going to give us representative data for the population. So we don't want to let the subjects choose whether or not to participate. But maybe we should let the researchers decide who gets to participate. Should the students who want to gather information about food in the calf, should they get to choose who gets to be included? Well, that's not exactly a good idea either, because we might tend to choose individuals that we know well, that are convenient for us to sample, people who are in our classes, people who are in our teams, people who are in our social group. And so uh, we can't, it could be that the people that we associate with might tend to have opinions similar to ours. And so we might not get a wide range of opinion. And so we might call this a convenience sample when we choose those that are most easily accessible to us. And that's not really likely to result in representative uh, opinion as either. So we don't want to let the subjects choose to participate. We don't let the research choose who gets to participate. What should we do? Well, I would suggest that what we should do is we should let random chance decide who gets to participate. So what we want to do is somehow uh, get a what we would call a random sample. If we if we let random chance decide who gets to participate, then it's much more likely that we're going to get a sample that represents the entire population. One primary type of random sampling is called simple random sampling. And so let's take a second to read this sentence here. If you take the sample so that every set of subjects in the population of that size has the same chance to be the sample selected, we're doing what's called simple random sampling. So let's take a minute to pause on this. Every single group of a particular size has the same chance of being selected. If that's the case, then we have simple random sampling. There are plenty of sampling options, random sampling options that are perfectly valid, but that aren't simple random sampling because they don't allow every single possible set to be chosen. But in the case that where every set can be chosen, that would be called a simple random sample. So one way to think about this in our head maybe is every individual in the population gets assigned a ticket or a number, and we would put that number on a bunch of tickets, throw them in a box, and if we chose a collection of n tickets one at a time without replacing the tickets in that after we've chosen them, we would have a simple random sample. So we'd be drawing a set of tickets from a box at random without replacing the tickets. That would give us a simple random sample. Any group of n people from the population would be eligible to be chosen using a method like this. So here's a scenario. We want to decide, is this a simple random sample or not? So suppose we had 24 students in our class, and we were all in class one day, and the students were arranged in 4 rows of 6 students. And I wanted to choose a set of 4 students to serve on some sort of advisory committee for me, to give me feedback on how things are going in the class. And I wanted to choose a simple random sample, which I hope would be a representative sample of the population, which in this case is the set of students in the class. Suppose that what I did was I went to the first row and I picked one student at random. I just I thought of a number between 1 and 6, and I used that to pick a person out of the first row. Chose a different number between 1 and 6 to pick a person out of the second row. Got another person from the third row, another person from the fourth row, all of them at random. Would this be an example of a simple random sample? So you might want to pause the video right now. Think about this before you go to the next slide. You know, is every single group of 4 students equally likely to be chosen in this scenario? Okay, well, I'm going to go to the next slide where we have the answer. And I want to point out to you that this is not a simple random sample. And that's because there are plenty of cases where there are sets of students that cannot be chosen. For instance, I couldn't, but just by random chance, choose all 4 students out of, say, the second row. Or I couldn't choose, as I've got here on the slide, I couldn't choose 2 people from the first row, 1 from the third row, and 1 from the fourth row. Those have no chance of being selected if I'm purposely choosing one student from each row. So while it's a perfectly valid uh, sampling method, it's not a simple random sampling method. If I wanted to do a simple random sample for collecting a set of 4 students at random from the group of 24 students, I could just assign every student number 1 through 24, put those slips of paper with those numbers on it in a box, pick out 4 of the numbers, and that would be my advisory committee. So notice the line in italics at the bottom of the slide. We're going to assume that any sample that's chosen at random in this course is a simple random sample unless we're told otherwise. So keep that in mind. Just briefly want to talk about 2 other sampling techniques, stratified and cluster sampling. The example that I gave you a couple slides ago, where we chose 1 student out of each row, that would be an example of a stratified sampling technique. I divided my population into groups or strata, and I chose a random sample from each of those strata. Here's another example. Suppose that I had, instead of a group of 4, I wanted a group of 6, and I decided that I wanted equal gender representation in that group. So then I would be stratifying my class by gender, and I would number all the males 1 through how many ever males I had. I would number the females 1 through all the females that I had. I would put each of those slips of paper in 2, all the males numbers in 1 box, all the females numbers in 1 box, and I could draw 3 male numbers from the male box, 3 female numbers from the female box, and that would give me a random sample, a stratified random sample from that scenario. So again, stratified randomly sampling, that's about dividing your population into groups before you do samples, and then you draw a random sample from within each of those groups. With cluster sampling, you're also dividing your population into groups, but in this case, what you're going to do is you're going to randomly choose a group and sample everybody within that group. So suppose that my advisory group was just going to be all the people who sit in 1 row in the class. Then I would draw a random number 1 through 4, and all the people, if my number were 4, then people in row 4 would be my advisory committee. Clustering sample also occurs in opinion polling. If we divided a large city up into, say, voting precincts, we might choose a few voting precincts at random, or a few blocks within the city at random, and we would survey everybody within those blocks that were randomly chosen. Okay, so random sampling, whether it's stratified or clustered or simple random sampling, is a good way to get a random representative group from your population. And if we can trust that the sample was chosen randomly in some fashion, we're going to be able to say meaningful things even from an observational study, even if it's not a causal relationship. So let's go on now and talk about the second type of study that's often done, and that's an experiment. And so in this case, the thing that distinguishes an experiment from an observational study is that in an experiment, each of the subjects in the experiment is going to be randomly assigned a value of an explanatory variable. And we're going to call this a treatment. And so we randomly assign subjects to different treatment groups, and within each group, everybody gets the same treatment. Different groups will receive different treatments, as I've said it here. So in the case of a randomized experiment, we actually are going to be able to draw some sort of causal relationship. So here's an example of an experiment. Suppose that we wanted to investigate the question, does taking an aspirin daily help reduce risk of stroke? So you've got 2 groups of people. We're going to randomly divide them into 2 groups. And so we'll just let random chance decide who gets in group A and who gets in group B. Group A, we're going to have them take an aspirin daily. And group B, we're not going to have them take an aspirin. We're just going to give them a placebo, a sugar pill, or some pill that looks like the aspirin but actually has no medicinal effect. And so the idea behind a random experiment is that if you let random chance decide who gets in the aspirin group and who gets in the placebo group, then on balance, we should expect that the 2 groups are going to overall look relatively alike, except for the fact that one group is taking an aspirin and the other group is taking a different pill, a pill with no effect. And so that's going to be the only difference between the two groups. Again, the random assignment to the groups is what's going to help us believe, it's reasonable to believe, that the only difference between the two groups collectively is what pill they're taking. Therefore, any difference in long-term stroke rate between the two groups would be assigned to the type of pill that they were taking. So an experiment often will lead to a conclusion of causality between the explanatory and the response variable. So I've said some of this already, but in an experiment, it's important to realize that researchers are manipulating the members of the population. They're manipulating what treatment they're receiving. And so we're trying to observe, does the difference in treatment lead to a difference in response? And so in this case, our explanatory variable would be the type of pill that was given to the subjects. The levels would be they got an aspirin or they got a placebo. And the response variable is also categorical, would be, we might call it long-term stroke status. And its levels would be yes, the patient did have a stroke at some point, and no, they did not have one in the long-term study. So I think I've used this term already, but subjects is typically the term that's used to represent the individuals that are participating in an experiment. They don't necessarily have to be people, although we often think of them as people. But we can have experiments that aren't performed on individuals that aren't people. And as I've used this word treatment already as well, those are the different values or levels of the explanatory variable. Typically, our explanatory variable will be categorical, but sometimes it could be numerical as well. And so the treatment groups are the ones that all receive. An individual treatment group will be the set of individuals that receive the same treatment. Some important elements of experimental design. One of them is control. One good meaning of the word control is that there's a control group in an experiment would be the group that either receives no treatment or the standard treatment. So in our aspirin stroke example, the control group was the group receiving the placebo. And so oftentimes we do this because we want to know, if we change the treatment from either nothing at all or what might be considered to be the standard treatment, do we get an improvement? Do we get a change? And as I say here, another element of control is having the researchers do all they can to make sure that there's a standard that's adhered to in how treatments are administered across all the treatment groups. As I've mentioned, randomization is vitally important. We've got to do whatever we can to make sure that our treatment groups are as alike as possible in all respects, except for the treatment that's received. And another important aspect of that is not only do we need randomization, but we need to have enough subjects in our study so that we can assume that not just by accident, a lot of individuals that have some common characteristic get assigned accidentally through random chance to one of the treatment groups. So we want to have enough subjects so that it's reasonable to believe that the only difference between the groups is the treatment that's being administered. And so I'm, again, summarizing this here on this slide. Observational studies often have confounding variables. We're using the random assignment to try to get rid of the confounding variables. So we often might call a random experiment completely randomized, in which case all subjects are in one pool and we're just assigning treatments at random to the populations at large. And so if we had, 500 people and we had four different treatment groups, we would completely randomized design would just assign to each one of each individual a random number between 1 through 4. we might try to make it so that each group has the same number, or at least roughly the same number. In that case, it'd be 125. So we might just say we're going to, the first 125 individuals we draw out of our pot get assigned treatment group 1, the second 125 get treatment 2, etc. So that would be a completely randomized design where everybody's thrown into one pot and we just randomly assign individuals to each treatment group from that pot. Another thing I've got here on this slide is about blinding. So an experiment is blind if the subjects involved don't know which treatment group they're given to or assigned to. So that's one reason why we would have the placebo in our stroke aspirin example, so that if we gave one group an aspirin and we gave another group no pill, then each group would know which group, each person would know which group they belong to. But if we give both groups pills, then they can't tell whether they're in the experimental group, the aspirin group, or the placebo group. But as I say, notice here as well, sometimes it's important for the researchers not to know which treatment each individual is receiving, in which case we would call the experiment double-blind. Double-blind experiments can be important because we don't want the researchers to subconsciously or otherwise think that, oh, I know this person's is in the treatment group or is in the experimental group. They're not getting the placebo, and so therefore maybe I'll subconsciously or otherwise give them a little bit extra attention, better treatment, and so you might actually get better outcomes for the group that's receiving a particular treatment if the researchers know who's receiving what treatment. So somebody knows who's getting what treatment. There's a code book, but the experimenters aren't in the know as to who's receiving what treatment in a double-blind experiment. Just want to briefly talk about one other type of design, randomized block, and this would be a case where we would divide our groups, divide our subjects into groups before we assign treatments. And as I say here, that's somewhat analogous to stratifying the population before drawing a random sample. Suppose that we thought that men and women might have different stroke risk in our aspirin stroke experiment. And so if we want to see if aspirin has a different impact on men versus women, we might block first by gender, and then we would have a men's aspirin group, a men's placebo group, and then a women's aspirin group and a women's placebo group. And so we would block by gender before we started. When should we block? Well, if we think we have a confounding variable ahead of time, we've done some initial research. We think there might be a confounding variable like possibly gender in the aspirin study. If men and women process aspirin differently, we might have a difference in response. But also blocking would occur when we don't have a lot of subjects. We have enough for replication purposes, but not so much that we might accidentally get a whole bunch of one value of a confounding variable in one group versus another. And so if we had several hundred individuals, then it's probably not going to be the case that we're actually going to get too many women, for instance, in the aspirin group, as opposed to not have them be relatively balanced. And so blocking generally is not that useful when we have lots and lots of subjects. So that's what I want to say about observational studies and experiments. And we'll go on soon to our next chapter where we talk about analyzing data.